Hello students, welcome to the course Network Theory. In the previous video, previous 4 to 5 videos, we understood what is meant by an Thevenin's theorem and we solved many problems, right? So today we'll see a new theorem called as Norton's theorem, so which is almost the dual of the Thevenin's theorem. Okay, so Thevenin's theorem is called as the voltage source equivalent circuit, whereas Norton's is called as the current source equivalent circuit. Okay, so as we have studied practical voltage source and practical current source in basic concepts, right? So that the same way this Norton's theorem is working. Okay, so just we'll look at what is meant by theorem, statement and proof, and then we'll see one example. Okay, so Norton's theorem, an American engineer E.L. Norton's at Bell Telephone Laboratories proposed a theorem similar to Thevenin's theorem. Okay, so Thevenin's theorem was done by Thevenin in the 1883 in the same laboratories. Same way, this Norton has proposed this theorem, which is almost equivalent to Thevenin's theorem. What it says, same way Thevenin's theorem statements comes. Any linear bilateral network, however complicated it may be, connected to a load impedance, may be replaced by a simple equivalent circuit, again equivalent circuit, containing a current source. Now, in Thevenin's it was voltage source in series, now it is a current source and an impedance in parallel with it. Okay, so this is the difference. So in Thevenin's theorem, there was an equivalent circuit containing a voltage source and an impedance in series with it. Now it is a current source and an impedance in parallel with. So any complicated circuit can be reduced to this form. So how we find out the current here? The current of the current source is equal to the short circuit current across the load terminals. Okay, so previously the voltage of the voltage source is equal to the open circuit voltage across the load terminals. Like that we used to define. Now current we are mentioning, and wherever open is there we will make short circuit current. Okay, and the value of the impedance is almost similar to Thevenin's. Okay, so which is equal to the equivalent impedance of the network as viewed from the load terminals into the network, replacing all the voltage sources by short circuits or internal impedances and all current sources by open circuit. So finding this impedance part is all same to same from the Thevenin's equivalent circuit. Only thing here is current. Okay, so current will be made if it is open circuit and it is shorted, and find out the current as we have done one of the cases in Thevenin's theorem also. ISC we have calculated, right? The same way this is done. Okay, so that's why remembering this is not difficult. If you remember Thevenin's, Norton's, same way you can write it. Okay, so wherever difference is there, that you have to just note down. Hope it is clear. So now we will try to prove this theorem. Okay, so again this theorem they will ask state and prove Norton's theorem. For that I am illustrating that. Okay, so this is the illustration. Okay, whatever I explained I have shown you as a picture. Any complicated linear bilateral network with a load impedance across this one will be formed as an current source. Now it is called as IN. Okay, because Norton, right? I suffix N I will use in parallel with an impedance ZN I am writing. Okay, and then load is there. This is the difference. Okay, so this figure B shows the Norton's equivalent circuit as seen from the terminals AB. If you see from here AB, okay, without removing the load, if you see, no, that is Norton's terminal. So imagine this is a circuit B as in Norton Thevenin's. Only this is there. So this is Norton's equivalent circuit. In Thevenin's, what you had? ETH in series with impedance. Now it is current source in parallel with impedance. Okay, so that is the idea. So since this is the dual of the Thevenin circuit, it is clear that so Zn is almost same as Zth. Okay, so it is looks like a source transformation circuit, right? So it is same, and In is nothing but here Vth by Zth. In is nothing but Vth by Zth. That means Ohm's law, V by R, right? So I is V by R is nothing but Ohm's law. From that it is Vth, Thevenin's equivalent voltage divided by Zth. So this is equal to this, this is equal to this. So that means if you have a Thevenin's equivalent circuit in the problem, so straight away you can find the Norton's just by doing this substitution. In equal to Vth by Zth, which is same. Okay, so that is the idea. Okay, so in fact, source transformation of Thevenin's equivalent circuit leads to Norton's equivalent circuit. Okay, so that is what I told you. This is also the same result. That's why in general, Thevenin's theorem is called the voltage source equivalent circuit, and Norton's theorem is called the current source equivalent circuit. Okay, So hope this is clear. So now we will try to prove this as a dual of Thevenin's theorem only. In that same fashion, we will try to prove it. It will be easy. Okay. So since you have done the detailed one in Thevenin's theorem, so we will show dual of that. Okay. No issues. So normally question is asked like that only. So show that Norton's theorem is dual of the Thevenin's theorem, or even if they ask state and prove Thevenin's theorem also, you can do the same way. Okay. Fine. So this is the not Thevenin circuit I have taken now. Okay, as a figure C. Okay. Previously I have seen figure AB. So ETH, ZTH. So this Z. Okay. Some cases I have written R. That's why there is a confusion. So ZTH it is in series, and there is a load ZL. Okay, and current IL flows across this. Okay, terminal. So now this is converted into an IN. So here plus minus is there. Okay, actually you can write like this: current source, reverse manner it is written. IN is upwards. Okay, normally conventionally current minus to plus will show like this. Okay, so it should be upwards. Make that correction, and then Zn will call. Okay, this Zn Norton's equivalent impedance, and this is ZL. So this is not going to change. So it will be removed and find out, and then it is connected back like this. So here we call this as IL, and here this we call it as IL dash. So now how we prove that is, so we'll apply an KVL here, and we'll get an expression of IL. Okay, in terms of IN and this load, all these parameters. Similarly, you'll find the KCL here for this, because it looks like a node here, right? So we'll apply KCL here, and we find the same IN current. Then we compare that. So if it comes same IL dash and IL, then we say it is dual. Okay. So circuit in figure C at terminals AB can be replaced by figure D, provided it is a source transformation. Okay, IN equal to ETH by ZTH. So this is the relation we are using. So this is the assumption. Okay, we are using. So from this, what is ETH? Nothing but cross multiplied IN. IN equal to, so 1 by ZTH. 1 by ZTH means admittance equal, right? So that is what it is used. So 1 by ZTH is nothing but YTH, admittance. 1 by R is there, G, that is conductance. Okay, like that. So that is written. So this statement is our basis for this calculation. Okay, so we'll make it as equation 1. So note down this, okay, diagram and this one. Okay, you can pause the video and note down. I will continue. So in the circuit of figure C, okay, so it should not be figure A, figure C here. Okay, confusion. Figure C we have taken, no? The load current. So first figure I am taking and drawing the doing the derivation. So it was ETH by ZTA plus Z. So when you apply the KVL there, so what you got here is, so ETH you had, okay, I have not written that equation, you are familiar now, minus current is IL in that branch, and the first resistor was ZTH. Okay, then minus IL into ZL, load current ZL, is equal to 0. This is the equation you will get, or else you will get another equation, minus ETH plus ILZTH plus ILZL equal to 0. Both are same. So if you take the IL grouping and if you take right side, so you will get the IL common, ZTH plus ZL. From that, IL is equal to, left side you have ETH, right? That's why it will come in numerator, ETH by the coefficient of IL will come in denominator, ZTH plus ZL. Hope this is clear. Have you got? So this is from KVL. Okay. Next, what I will do, so I will substitute for ZTH and ZL in terms of admittance. I will use this relation, ZTH equal to 1 by YTH and ZL equal to 1 by YL. Okay. In terms of admittance, I will write this denominator terms. I will take the LCM now, ETH by, so you will get YL plus YTH, and this YL YTH. Okay. So now I will simplify. So what will happen? I will take this YTH in the numerator. Okay. So ETH into YTH. Also YL will also come in numerator. So but that I will separate it and write it. YL by YTH plus YL. This is how the form I will write the equation now. So what is from equation 1? ETH into YTH is nothing but what? Norton's current, right? Equation 1. So just refer. So from that you got YL by YTH plus YL. So this is the equation number 2. Okay, important derivation about IL. Okay, from figure C, IL it is the relation. Okay, so for this you can write the reason here. Okay, from 1. You can write the equation from 1. ETH into YTH is equal to IN. Okay, how you got this? Hope it is clear. This part you can note down now. Okay, I will continue. You pause the video and note down. Next, I will consider figure D. Okay, so right side figure I had no. So figure D you make the load current IL dash. Now I am applying here IL dash. Okay, what I will do, I will use the current division rule. What I have used also you remember here. Okay, current division rule. Current division rule is simple, right? Because you have one current source there, IN, and you have the two impedances in parallel, right? One is ZTH, another is ZL, right? So this is the two you have. So you have to find the current in this branch now. So in this branch current you have to find means this is IL dash. Okay, this is IL dash, which is equal to total current is IN here coming to this node IN, opposite branch resistance, which is the opposite branch, that is ZTH, and we have told that ZTH is equal to Zn, right? So that's why it is written Zn straight away. Okay, or you can write in first step ZTH, okay, which is equivalent to Zn. So Zn I have written, and then Zn plus ZL, total resistance Zn plus here ZL. That is the current division rule. You can note down. Okay, how it came this equation, current division rule. Okay, so then again I will substitute it here again, because first cases I have shown you, that's why I have not shown again. So Zn you substitute as in terms of admittance 1 by Yn, and for ZL you substitute 1 by YL. Okay, so note down this. Okay, if you are not following, so take this and now take the LCM. So when you take the LCM and simplify it, so what you will get, so in the numerator you are getting this 1 by Yn, okay, into, so this if you write it in reverse manner, so you will have here Yn into YL. So in the denominator you have the Yn into YL divided by Yn plus YL, Yn plus Y. So this step I have not written. Okay, so you note down this step. So Yn cancel out. What is remaining? YL by Yn plus YL. So which is the equation number 3. So now just look at the equation 2 and 3. So what you will get? IL equal to IL dash. This is the proof. Okay, so very simple. So just go through once again if you have not understood the way I have proved it. Okay, so very simple. Here current division rule I have used, there I have used KVL. Okay, mesh analysis. So from equations 2 and 3, the load current IL dash may be made equal to IL in the circuit, but one condition we have proved it. What is that condition? ETH into YTH is equal to IN, and another condition is what? ZTH equal to Zn. That is the theorem, right? ZTH equal to Zn. These are the two proofs. So then the circuit in figure C and D. Okay, so C and D are equivalent. Make that correction. So here current IL dash is the short circuit current. The terminals are shorted here. So short circuit current at terminals A, B, and the ZTH or YTH is the impedance or admittance measured between the terminals with all energy sources eliminated, but not the impedances. Okay, so finding out Zn, Norton's equivalent impedance is same as Thevenin's, only current we are making short circuit current instead of open circuit voltage. Okay, so that is the proof. So now to understand this, we will take one problem here. So remaining problem we'll do in next video. Okay, so before that, the same procedure I will show you. There are three kinds of cases will come when finding the Norton's equivalent circuit. So finding IN, okay, Norton's current is not a different one, which is same. Okay, whereas uh, impedance is changing as in the case of Thevenin's. Okay, so no much new things. Okay, if the network contains resistors and independent sources, then we'll deactivate the sources and find Rn by circuit reduction techniques, series, parallel, star, delta, whatever combination. Okay, so then I will find IN with sources activated. Okay, with activation. So that way I have shown. Second case, if the network contains resistors, independent and dependent sources, now then we have to follow different steps. So then we'll determine the short circuit current ISC, which is nothing but the same IN, okay, Norton's equivalent current with all sources activated. Then I will find the open circuit voltage. So I will open circuit that terminals and I will find VOC. This is the additional one. Okay, VOC will find as we have done in Thevenin's. Then we'll take the ratio of that VOC by ISC. So even in Thevenin's theorem, second step we have done the same way, right? So open circuit voltage VTH was there. ISC we have calculated by short circuiting. Remember that? Okay. So that is the same way for Norton's here finding RN. Okay. VOC by ISC. What is the third case? You can tell now. What is the third case? When you present with only dependent sources and resistor. If the network contains only resistors and dependent sources, there is no energy sources, then what will happen? No energy source means IN is 0. Okay. So what you will do? You will connect a 1 amp current source to the terminals AB and you will find the voltage across that terminals AB. And then you will take the ratio of VAB by 1, which is nothing but the RN. Even another also you can do, you can connect a 1 volt voltage source to the terminals AB and you can measure the current flowing from B to A, okay, current IBA, and you can take the ratio 1 by IBA, that also Norton's equivalent circuit, okay, Norton's equivalent resistance RN, okay, that again I have not explained it, okay. So finally a note, since VTH equal to VOC and IN equal to ISC, remember this. Okay, open circuit voltage means VTH, short circuit current means it is Norton's current. Okay, so RTH is always ratio of this VOC by ISC equal to RN. Okay, so this is the idea. The open circuit and short circuit tests are sufficient to find Thevenin's or Norton's equivalent circuit. Okay, so hope it is clear. Okay, so what is meant by Norton's? If you know one theorem, another theorem easy. Okay. So with this, we are completing the statement and proof of the Norton's theorem. So now we'll solve set of examples, problems one by one. Okay. So I will solve one problem now. Okay. In the next video, I will take the remaining problems. Okay. Note down the first question. Find the Norton's equivalent circuit. Norton's equivalent circuit for the circuit shown in figure below. Find the Norton's equivalent for the circuit shown in figure below. So you have a 4 ohm, 24 volt, 3 amp, 12 ohm, and terminals are opened here. No load is connected. Just you have to find a current source in parallel with impedance or resistance. You have to show, that is the Norton's equivalent circuit. Okay. So what we have to do now? So what is the procedure as per theorem? So to find the current of the current source, first is IN you have to find out, right? So for that, what you have to do? You have to short these terminals AB and you have to find the ISC current in that. Okay, so we'll do that part. So that is the first step. So hope you have noted down the question. To find IN, short the terminals AB. This results in a circuit diagram as shown below. Okay, so this was all given. Just you write down one more time the network, and now you short the terminals AB. In the question only, don't do that. Write it once again. Okay, otherwise you will confuse. And this current is A to B is called as ISC now. Okay, so now if you look at the circuit, so all are at the same potential. This is at the same potential, which is A, right? So I call this voltage as VA. So now I will apply the KCL here, or nothing but node analysis I will do. Single node is there and this side it is reference node. Okay, ground potential. And one more thing here is, so if you have a closed path, short circuit and a resistor, so what is the answer of this? It is always a short circuit. Okay, so this resistor does not have any current or voltage. Okay, so that's why it is like a nil. Okay, does not have any effect. Same way in this branch now. Okay, so now apply the KCL at node A. So I have directly written it. So you want, you write the equation here. I will write. So in node analysis, we will take the assumption that all the currents are leaving the node. Okay, so all the currents are leaving the node. Okay, so now if we consider same way, so this is 24 by 4. Okay, it is 24 voltage by 4. That is the current, right? Voltage by resistance. Then here you have the current entering the node. Okay, so that means what? It is -3. and there is no current or voltage in this branch. I am not considering. I will consider this ISC branch. Okay, so which is leaving, that's why it is plus ISC equal to 0. Okay, is there any changes happened here? ISC minus 3. Okay, so this was flowing here, so normal direction, this was flowing here, and we have assumed it is opposite, so that's why it is minus 24 by 4 it should come. Okay, minus 24 by 4 minus 3 and then plus is equal to 0. If you take this right side, so what will happen? Is equal to, these two becomes plus here, minus 24 by 4 plus 3, it is correct. So this is 6, 4 6 6 plus 3 9, so ISC is 9 amps, which is nothing but the Norton's current. Hope it is clear. So as we do problems, so the things will clarify. Okay, so since it is short circuited, no need to consider again this as VA by 12. Okay, because there is no voltage flows here. Okay, so which is because of the short circuit, and also here current is there already in this. Okay, 3 amps, so it is considered because this is a current source equivalent circuit here. If you convert this into a voltage source, what will happen? If you convert this, what will happen? 3 into 2, V equal to IR, right? 3 into 2, it is plus, head side plus minus 6 volt into series 12 ohm, right? So this is going to come. We can replace this branch by this, so then you will have only 3 branches. Clear? Then you write that same way, it will be minus 6 by 2 you used to write. Instead of 3, you write minus 6 by 2 and this branch the same way. Okay, so when you have current source in parallel with resistor, so no need to consider again separately in the node analysis. Okay, so careful about this. Fine, so we'll go for finding now Zn, right? That is the Norton's equivalent impedance. So that is same. So you have only two independent sources are there, just deactivate that. Current source means it is open circuited, voltage source means it is short circuited. Okay, so that will do. To find Rn, deactivate all the independent sources resulting in a circuit diagram as shown below. So when you remove the current source, it is open, voltage source, it is short. So you'll have 4 ohm and 12 ohm in parallel now. Okay, so this is the parallel connection. So just find out R1, R2 by R1 plus R2. 4 into 12 by 4 plus 12, it is 48 by 16. So 16 3 is a 48, 3 ohm. No need of calculator also. Okay, so Rn you got 3 ohm. So thus Norton's equivalent circuit is 9 amp in parallel with 3 ohm. So this is the answer. Simple. Okay, so don't confuse with Thevenin's. Okay, Thevenin's you are open circuiting the voltage and looking at the applying the finding the voltage across the last, okay, across the element which you are having. Okay, here it is current. Okay, short circuit current you are finding and you are right. Clear? So it is 9 amp in parallel with 3 ohm. Okay, so to more clear, so we'll solve more examples. Okay, so in the next class we'll take another 2 examples like that. Next same way we'll proceed with the Norton's theorem. Another 2 videos we'll discuss Norton's theorem problem. Okay, so go through once again. Again you have studied a new topic today, Norton's theorem. At a time you may not understand, so recorded video is there, so just go back and listen once again, note down once. Okay, so if you have any doubts, note down and you can clarify. You can come. Okay, I have put the message already. You can come after 11 any working days. Okay, thank you. We'll meet in the next video.